Good morning or good afternoon, depending on where you are at. My name is Ataro Azizi Namini, Director of the ABC UTC at Florida International University. We also want to share with you that there is a very short video capturing the highlights of our last ABC conference, the 2022 International ABC Conference that was held in December in Miami, Florida. It captures the highlights of the conference. So if you go to our website, go to the conference page in the archive section, and you will see the video. It's a very nice video, really, for those of you attended or did not attend to see the highlights. Also, we would like to remind you that it may seem a long time from now, but the time passes very fast. Our next conference is going to be in December of 2024. The location is going to be different than the hotel that we've been using, most likely. And also, most importantly, the next conference will be devoted to general bridge engineering, with emphasis on the innovation in the bridge engineering. So stay tuned for more information to come.
Our presentation today features the AASHTO and Precast Prestressed Concrete Institute Northeast guidance on precast substructure connection details. We're pleased to welcome our presenters, Mike Culmo, Chief Bridge Engineer with CHA Consulting, Inc., and Rita Seraderian, Executive Director of PCI Northeast. Also would like to introduce our Q&A session moderators, Paul Lyles, formerly Georgia State Bridge Engineer, and Jugesh Kapoor with WSP USA and formerly State Bridge Engineer at WASHTO. We'll now begin the featured presentation. Mike?
Thank you. It's a pleasure to be here today to talk about precast substructure connection details, talk specifically about a document shown on the screen that is published by the PCI Northeast Bridge Tech Committee. Joining me, Rita Seraderian is the Executive Director of PCI. She is the chair of the committee that develops this document and many other documents that we'll talk about. The outline of what we're going to cover today is the background of the committee, where the committee started and where we've come. The second thing we'll talk about is a little bit of the history of the committee and some of the ABC resources that are developed. Then we'll dive into the main topic of today's presentation, is to talk about the 2018 AASHTO LRFD guide specifications for ABC. And then we'll dive into the guidelines for precast substructures used in ABC that was prepared by the committee. I'll turn it over to Rita now to talk a little bit about our committee.
Thanks, Mike, and thank everybody for letting us host this presentation today on the guidelines that the PCI Northeast Committee had developed. It was published last year, and today's webinar will go into much detail of the document and how to use it. But I want to give you some background first on the Bridge Committee that actually helped develop this document. It was established back in 1990. And originally it was just Massachusetts, Connecticut, and Rhode Island. Focus was actually updating bridge standards at that time. Most of the DOT's bridge standards had been pretty old, and they wanted to make them consistent across the 3 states. After that task was complete, we actually had Vermont, New Hampshire, and Maine, and New York join the committee, and we began to start working on regional documents that all of the states wanted to use. And I will be going through a couple of examples of those documents here in a second. But so there's over 30 people that are part of that committee, which is made up of DOTs, consultants, precasters, and actually academia too. So it's been a robust committee, pretty active. We meet 2 to 3 times a year in developing the material that I will go over. And we also have task groups that kind of focus in on certain documents to get them done on a relatively short period of time. So just a quick history on ABC. We tackled this subject starting back in 2002, when it was starting to kind of rumble out there in the marketplace. We wanted to get ahead of it, and we knew that precast would be dominant in the ABC market. So we wanted to provide as many resources that we could actually develop regionally. And the first document we developed was on full depth deck slabs. From there, we went into actually developing the first document, and Mike's going to go into the history of the ABC guidelines on his slide. But I do want to mention that we also developed the next beam, which a bunch of states now use. We also developed additional details for approach slabs. We also developed the deck bolt T guideline, which has been used on several projects in this region. And then finally, we also updated a non-conformance document that we found that was very valuable to a lot of the DOTs that had questions on anything that had potential issues and how to repair them. The Camber Profile Management document is also a relatively new document. So where do you find all these documents? If you go to the PCINE.org website and click on Technical Resources, this is where all these documents live. If you do go to PCI.org, you won't find it, unfortunately, will not find these documents there. So once you click on the Technical Resource tab, it will open up and it'll show you next beam, accelerated bridge elements, Northeast Bolt T, and deck panels. So depending on what you're looking for, if you click on the Accelerated Bridge Element tab, it will open up a window, and that's where you will find this document. You will also find many other resources listed under that same page. So again, during COVID, our committee was pretty busy. We updated the full deck panel guide in 2020. The next beam guidelines have also been updated. There is a link, by the way, to ADC UTC's implemented advanced technology page. So if you actually do find my document there, it is the current one. It is linked, so it'll always be current. And then finally, today, we're going to be talking about the precast substructures used in ABC document. And with that, I'm going to let Mike Culmo take over, give you a little background on where we are with this document.
Thank you, Rita. A little pitch right here for training modules. A lot of the details we're going to discuss today, we always get questions on, well, how do I design that connection? How do I design that element? NCHRP Project 12-102A included the development of training PowerPoint slides, training modules for all types of ABC components and elements. So a number of times today, I'll refer to this website. You can do a search on 12-102A and find it, and you can download PowerPoint shows with audio narration at your leisure. And these PowerPoints include design examples for virtually everything we'll show today. So a little bit, as Rita mentioned, the committee has been very involved with ABC from the beginning. We kind of jokingly say we were involved with ABC before ABC existed. Not really true, but it was in the early days. And one of the first documents that we published was in 2006, Accelerated Bridge Construction Guidelines. At the time, it was the only significant ABC document out there. In 2012, we issued Precast Substructure Guide Details. We wanted to have details and drawings because people were asking for details. How do we actually implement ABC? These guide details were based on the use of grouted couplers at that time because that was all that was available for connections for the most part. In 2014, we decided to upgrade and produce the second edition of the Accelerated Bridge Construction Guidelines. We added a bunch of things to the document at that time to bring it more up to date. But then in 2022, we developed guidelines for precast substructures using ABC, and this is the document I'll be talking about primarily for today. So in the midst of all that, in 2018, there was a very important date that in 2018, AASHTO published the LRFD guide specifications for accelerated bridge construction. What we found as a committee is many of the items that were in our document, our accelerated document, was also included in the AASHTO document. But this AASHTO document can contain many new connection details that we did not cover, things like UHPC, pocket and socket connections, and lap bar reinforced connections. The AASHTO guide spec, these are the sections that are in the guide specification. There are 5 devoted to design and 7 devoted to construction. Not the intent of this workshop to go through this document. We've had other workshops covering this, but really this just gives you a flavor for what the AASHTO guide spec covered, which is just about everything in ABC design and construction. So in 2020, our committee sat down and looked at what we had and realized, in 2020, we issued updated full depth deck panel guidelines. The industry had moved forward. There were new details out there, better details out there, including UHPC, the concept of running panels longitudinally. That was something that was done in Boston and other states. The problem we had was our ABC guideline had deck panels. We had now had duplicate documents with deck panels, and that was an issue. So our 2014 guideline, we had some issues with it, that the majority of the provisions in that guideline were covered in the AASHTO guide spec. So we had duplication there as well. Our full depth deck panel guidelines were published. We had duplication there. So really, if you take those things out, really all that was left was substructures, but all of our substructures, our details were based on the use of grouted couplers. So our decision was made by our committee to remove all the redundant text that was in the AASHTO LRFD guide spec, remove the full depth deck panels, but then add details for the new connections that are covered in the AASHTO guide spec, and then convert the previous guide to really just a substructure guide. So in 2022, this new document was born, entitled Guidelines for Precast Substructures Using ABC, published May 13th, just last year. It's available for free. Rita didn't mention all of the documents she talked about and are available for free at PCINE.org. So let's dive into this document and see really what it includes. As I mentioned before, the ABC guide spec had a lot of text in it that was redundant for what we had in our previous guide, but there were certain sections in our previous guide that were not in the AASHTO guide spec. So those moved over into these sheets. These are guideline sheets. There are 4 of them that give guidance on ABC, especially with respect to substructures. So we'll just walk through these provisions rather quickly. You can download this and read it at your leisure. So the first section is an introductory section, which just talks about the fact that this document is based on the AASHTO guide specification. The next section talks about designer responsibilities. This has to be clearly stated because there's a lot of work done by the fabricator on ABC projects and the contractor in order to make sure it was clear what the designer was responsible for in the design of a precast substructure. We include special notes to the designers, and the note here is noting that the details included are schematic. They are not exact. You can't just copy them, put them in a project, and put it on the street. That you actually have to design connections and design the reinforcing in the elements. That is all covered in the guide specification for ABC, so there's no need to. So we had to make sure we make it clear. You still have to design the bridge and the connections. We have a section on geometric configurations saying, well, in a perfect world, we'd like to keep everything 90 degrees. We understand that's not the case, but if you have a choice, it's preferred to keep things simple to make it less expensive and easier to construct. Tolerances are so important in precast, especially in substructures. NCHRP had a project 12-98 that produced a document entitled Proposed Guidelines for Prefabricated Bridge Elements and Systems Tolerances. We recommend the use of that document, which is available for free through NCHRP. The details in this guideline we're going to go through today include tolerance notes and tolerance details based on that document. We give some guidance on shipping and handling, just general rule of thumb on the size and weight of a typical precast element that is easy to ship. You can go beyond these limitations. It may require special shipping, but we wanted to give a little bit of guidance to designers when they size elements. The next page, sheet 2 of the guidelines, we have a section on special materials and devices, specifically talking about the use of corrugated metal pipe voids, which we use quite a bit in substructures, grouted splice couplers, leveling devices, and then non-compressible shims. There were a few questions before this webinar about spread footings, so we have some guidelines for construction on bedrock, construction on soil, and construction on piles. I'll show those details a little later in the presentation. Grade control is very important. We do recommend the use of grade adjustment devices, either cast-in leveling devices or shims, to make sure that we hit the grades that we specify. Then materials. There's a lot of materials used in ABC, and we have a little section on each one. First, precast concrete, which is pretty straightforward. Secondly, we talk about side cast concrete and grouts, and how side cast concrete are used mostly for connections and for closure joints. We have recommendations for mixes for site cast concrete, where we define very early strength concrete, and conventional concrete. We talk about controlled density fill, which is also called flowable fill, and we'll show details where that is recommended to be used, primarily underneath spread footings. Grout. Grout is a common material used in ABC, so we have a small section on grout for grouting smaller voids. Page 3 of the guidelines, and then we get into joints and connections between elements. And we talk about structural and non-structural connections. Non-structural would be things like shear keys or expansion joints, but really for the most part, we're talking about structural connections between elements. We have some guidance here on vertical joints. We have had cases where tall vertical joints have been difficult to form, where they using a simple backer rod can fail due to the pressure of the grout as you install it. So we have recommendations for putting notes on plans for forming tall vertical joints. Design of connections, everyone asks questions about this. Unfortunately, the AASHTO LRFD guide specifications for ABC has provisions for all the connections we're going to show today. And the training videos or training PowerPoints that I mentioned before is also a resource for learning how to design these connections. And we'll cover that today as well. Construction specifications, as you recall, the AASHTO guide specification includes provisions for construction specifications as well as design. We added a little blurb about repair of nonconformances during fabrication. It's inevitable when you make large precast elements that there may be some minor damage due to shipping and handling. Fortunately, as Rita mentioned, we have a document that covers how to address nonconformances in precast. And then references. The basis of all we're going to show you today are these documents. Primarily the AASHTO guide spec for ABC is a big one. But then PCI has several documents that we use to develop this as well as some federal highway manuals. And again, as I mentioned before, NCHRP Project 12-98 with regard to tolerances. Enough of the text, but let's get into more of the detail. This is a detail usage table that's on page 6 of the document. It is a very useful thing, a starting point if you're looking to develop a design for a substructure. So let's zoom in on this first corner here, which we have for every detail. We've developed details for all these connections, and we've assigned detail numbers to each detail. In this case, G1, which is a grouted coupler connection for precast columns or walls. This is a hyperlink. The blue text is a hyperlink. If you click on this, it'll bring you to sheet 8 of the document, which will include those details for the grouted coupler connection G1. On the second column is the detail usage reference. And these are the sheets, it's like an index. These are all the sheets within this document that show the use of that coupler connection. So sheet 1, 2, 3, 4, 5, and 6 include places where you can use this connection. We also included a section on advantages and design construction considerations. You might look at design and construction considerations might be taken as a disadvantage, but really we just wanted to make sure designers knew the pluses and minuses of each connection we're talking about. So the key here, this table is really the central starting point for any design to get you where you need to be. So let's take a look at the guide details. This document is chock full of details. And if you recall from previous slides, we showed a similar detail for, this is a framed pier bent, that show grouted couplers in all the connections. Now you'll notice the big change here is there's no grouted couplers shown. And the reason why is there are now many different connections that can be used for these connections in addition to grouted couplers. So let's take a look at some of the details. First, we'll focus in on this column to footing connection at the base. You'll notice here that note says column to footing connection. Options include G1, G2, P4, P5, and S1. That means we now have 5 potential options to connect this column to the footing. So if designers don't like grouted couplers, you have options. You can go to pocket connections, which P stands for pocket, S stands for socket, RC stands for reinforced concrete, and K stands for keyed joints. Let's take a look at this section of this detail. We talk about tolerances. As I mentioned before, tolerances are very important. So we've included erection tolerances, in this case for columns. We note that all tolerances should be measured off one common working line. And then we have tolerances below as well. Now we also have tolerances in the transverse direction. So take a look at this detail showing that the erection tolerance for the cap, the column, and the footing is measured off, again, a common working line in the transverse direction as well. And these are the way that we recommend a precast pier be detailed on plans showing these tolerances. Really importantly, at the bottom of each sheet in the title block, we have a couple of very important notes here. The first note is highlighted, anything that's highlighted in the drawing that I showed you before is hyperlinked in the file. So if you see a particular connection that says you can use a P1 connection, you click on that P1 and it brings you to that detail sheet that includes the P1 connection. Also in each sheet, we have a return to the detail usage table. This is a hyperlink that will bring you back to that table I just showed. So now let's take a look at wall piers. We included pier bents. Now we're looking at wall piers. Let's take a look at this detail in the bottom left corner. The key thing we like to point out here is that we're using corrugated metal pipe voids to reduce the weight of the piece, and also we can use it for certain connections that we'll go over today. Once the piece is erected, the pipe voids can be filled with normal concrete, as shown here. Okay, now we'll take a look at the cap on the upper right. Zoom in on that. We'll be going over the concept of using a precast wall cap element. It's a way of building precast that really simplifies most of the fabrication. And again, we're showing, in this case, 4 different potential connections to connect that cap to the wall below. Down the footings, we offer 2 different options for footings. You can either use the reinforced concrete closure joint, or you can use a grouted shear key if you desire. Both options work. It's really designer's choice. Now we're jumping into integral abutments and semi-integral abutments. So we'll take a look at the upper right detail first. This shows an integral abutment connection, and there's a few things to point out here. We have a pile to stem connection. In the world of AASHTO, this is referred to as a socket connection. We also note that the connection of the back wall to the top of the cap can either be integral, meaning it's cast integrally with the stem, or it can be a grouted coupler connection as well. So we give options there as well. Looking at the lower right detail, we have a semi-integral abutment connection, and we're showing this semi-integral abutment on essentially a soldier pile wall down below. It can be a conventional cantilever abutment. It doesn't necessarily have to be this particular soldier pile detail, so they both work. Now we'll take a look at the joints between elements. Early integral abutments built with precast concrete were built with transverse post-tensioning, which is perfectly adequate. It's a little slower, a little more difficult to build. So the committee decided to hone in on using grouted key joints between these elements. As long as there are at least 2 piles in each wall stem, this is a structurally adequate way to make an integral abutment. Joints K1 and K3. Now let's look at cantilever abutments, which are very similar to wall piers. The only difference is there's soil on the backside. Otherwise, it's very similar. Let's take a look at the upper right. Again, the same concept of having a precast cap element connected to the wall elements below, and the same thing with the back wall, where it could be integral or a grouted coupler connection. So here's some photos showing what that might look like. The photo in the lower right is a X-ray view of a precast abutment, where the wall panels are all very simple, easy details and easy things to fabricate. And then the concept is to use one complex cap element where the bridge seat is in the back wall. And the idea here is to make one element difficult and all the rest of the elements, meaning the majority of the elements, are simple. The detail shown in the X-ray view is a wall panels connected with grouted couplers, but as we showed before, there are multiple options for making that connection. But really, it's cool to see on the left are 2 photos from a bridge built by Maine DOT in Kittery, Maine, where this concept was executed, and you can see the precast wall elements below and the cap going in on the top. Very attractive looking abutment that was very successfully built by Maine DOT. So just an example of what this might look like. This is from the Federal Highway had issued LRFD design examples in the early 2000s. So we took that detail out of the design example and we essentially reverse engineered it in precast. This comes out of those training PowerPoints that I was mentioning before. The idea here, again, simple wall panel, more complex cap element. In this case, cast in place footing. We'll talk about that in a minute. So the little typo here, it should be say wall to cap connection concept. And the idea here is to keep this wall cap, it's a wall cap concept. Again, keep the cap complicated, but keep the wall elements simple. And so you have one complex element and a whole bunch of simple elements that'll reduce the price. Now, the key thing is connecting these 2 together is a very simple connection to design because there's very low moment demand that high up on an abutment, especially when you factor in the weight of the superstructure. So this is a blow up showing that detail, showing how that might work. And the concept here is to use the corrugated metal pipe void with simple dowels between the 2 elements to make the connection. Here I've highlighted the NCHRP Project 12102A training module number 2 covers calculations for this connection. And what you find out is that you really don't even need the reinforcing bars, that there is no tension across that connection, which is kind of similar to an old stone abutment that has just grouted joints between stones, and they've lasted over 100 years. And this the calculation proves why this is the case. As far as footings for an abutment, there are numerous options available, as I mentioned before, but one that we've kind of honed in on, especially if you have a pile-supported abutment, is using cast-in-place footings. It's very difficult to make a precast footing connect, excuse me, to piles. We have found that there are details that have been developed across the country where we can do a cast-in-place footing and still use a precast stem. And what's great about this is the design of this connection is the same as cast-in-place concrete. It's just essentially building the bridge upside down, building the stem before we build the footing. So very simple design. And then the stem, we use corrugated metal pipe voids to reduce weight. If you fill the CMP pipe with concrete, the design of the abutment stem is unchanged from cast-in-place. So let's get into retaining walls. This is sheet number 6 of our document. Different retaining wall options are presented. We'll first look at this one here, which is probably new to most of you, which is the concept of essentially a counterfort retaining wall, where we have a fairly thin wall face, and then we have bump outs behind the wall face that have corrugated metal pipe voids. The concept here is connection P5, which is shown between the footing and the stem, where reinforcing bars project out of the footing into this void to make the connection to the footing. Very simple connection. It's a pocket connection that can be easily designed, essentially the same as cast in place. So these bump outs, these build outs on the back side receive the footing reinforcing bars. Next detail we'll look at is the soldier pile wall detail on the bottom. Very similar. Instead of having reinforcing projecting from a footing, we essentially connect these precast wall panels to piles that are either driven or drilled or in place. Essentially a simple soldier pile wall. It's a good option for relatively short walls. If the walls get tall, you can add soil anchors, as you would with any soldier pile wall, to hold back the soil forces. And this is a socket connection, S2. There were questions in the pre-webinar about footings, so let's go through this a little bit. The first thing we want to talk about is leveling devices. In our previous document, we included mechanical leveling devices, which are shown in the upper detail, which is perfectly fine, but they can be expensive. Contractors and our fabricators on our committee noted that it's really just as easy to put non-compressible shims to set grade and to set these footings ahead of time. So we do recommend that. You'll notice underneath these footings, the note says flowable fill. For spread footings, we do recommend flowable fill. And the reason for that is, well, I'll back up. Many people have designed these with non-shrink grout between the footing and the soil, or the subgrade. The reality is the soil pressures on the bottom of typical footings is in the range of 100 to 200 PSI. So we don't need a 5,000 PSI grout to take that force. Flowable fills typically have strengths in the order of 1,000 to 2,000 PSI, and it's perfectly adequate for spread footings. We have a detail for a reinforced closure joint between footings, and the idea here is that you can make your footings smaller and connect them in the field rather easily using extended reinforcing bars from one footing to the next. Again, flowable fill used underneath the footings. Now, grouted couplers, we still include grouted coupler connections. They are very robust connections and they're very applicable to many locations. So let's take a look at the details. We have two G1 and G2 grouted coupler connections. One is inverted where the couplers are in the footing, which is handy for seismic applications where you want to get the couplers outside of the hinge zone. And in G2, where you don't have that issue, you can put the couplers in the column. We have details for both. This sheet now shows grouted coupler connections for pier caps. The first one, we'll take a look at the one in the lower right. And the key thing I want to point out here is that it's very important to lay out the couplers in consideration of the reinforcing in the cap. You may have to move the bars around in the cap to get around these couplers, so it's something that really should be done. On the right, we got a nice photo of a precast cap being installed. This is in Holyoke, Massachusetts for a Mass DOT project that was built using grouted couplers. So as far as designing grouted coupler connections, a grouted coupler has the same strength as any mechanical coupler in AASHTO. As a matter of fact, the ABC guide spec has a higher level coupler called the Type 2 coupler that is actually stronger than a typical AASHTO coupler. The graphic on the lower right, 3644, is a little snippet taken out of the AASHTO guide specification. These can be used in certain seismic applications. The key thing with designing a coupler is it's treated just like a lap splice. You design your reinforcing just as if it's cast in place. There is a design example in the NCHRP 12102A training, module 2, that covers these connections. The key thing with the design is the couplers are larger than the bars, so you have to move the cage in a little further into the element, which reduces your effective D of the design. Aside from that, the design is the same. Now we're going to get into some of the newer connections that came out of the AASHTO guide specification that were not previously covered in this document. This is a detail for pocket connection P1. Now, pocket connection is defined by AASHTO is when reinforcing from one element projects into a pocket or void in the adjacent element. In this case, we have a column with reinforcing bars projecting from the top of the column into a void in the cap element, and this void again is made with corrugated metal pipe. So here's a close-up detail showing that. You'll see the photo on the right is from the research that led to this document. This is a seismic connection. This is valid for high seismic zones. Back up, the key thing is the reinforcing in the cap projects through the void, both in the bottom and top. So again, you have to be careful about your reinforcing layout to make sure the bars don't interfere, the column bars don't interfere with the bars in the cap. The key thing that's cool about this connection, in many cases, the corrugated metal pipe void can function as your confinement reinforcing for the cap design. Again, this is all covered in the AASHTO guide specification. One thing that's important, people always ask, how big should we make this void? And tolerances really drive this decision. So we developed this. This came out of the NCHRP 1298 research, and we have an equation for the recommended minimum pipe size based on tolerances that are given. As far as designing pocket connections, the two graphics shown on the right are snippets from the AASHTO guide spec. This connection is fully specified in that document. And it's a fairly detailed design procedure, but again, the NCHRP Project 12102A training, Module 2, goes through a full design example of this connection. Now we'll move on to another type of pocket connection. This is a P2 and a P3 connection on this sheet. A little bit similar but different. In this case, instead of having one large pocket, we have multiple smaller pockets that are made with post-tensioning duct. And this is a fully researched connection that does work for seismic as well. Again, you should lay out the reinforcing in the cap to make sure those post-tensioning ducts do not interfere with the reinforcing in the cap. As with the other pocket connection, we give recommendations for how to calculate the size of the post-tensioning duct required based on the anticipated tolerances to be used. So as far as design of this connection, again, it's covered by the AASHTO guide specifications in Article 365. And these two boxes shown here are snippets from the AASHTO guide specification. The next detail, P2, another pocket connection, we've already shown it before, is where you say connect the cap to a wall panel using dowels in a corrugated metal pipe void. Again, here's a nice photo from the Kittery main bridge showing that cap. You can see the dowels projecting from the wall element below into the cap. And once the wall cap is set, you have ports on top of the cap to pour in concrete or grout to complete the connection. Okay, the next connections are connections P4 and P5. These are additional pocket connections. So let's take a look at the one on the upper right. I love this detail because it's so simple. Essentially, we take a precast wall element with a temporary support cast into it, set it on a leveling pad, and then we essentially pour the footing around the bars projecting from the wall element. Very simple cast-in-place design. It might take an extra day to build this as opposed to using full precast for the footing, but it's a much easier detail to execute in the field, and it's a much less expensive detail, and it really is still quite fast. The detail on the lower left is a sketch showing how this might work for, say, a wall pier construction. This next detail, I'll give credit where credit is due. Maine DOT, that Kittery Bridge, they use this detail too, where they actually took a cast-in-place footing and had reinforcing bar clusters sticking out of the footing, and then they set the wall element on top of the bars using the corrugated metal pipe voids to connect the two. So here's a photo showing that. The wall element, again, it's a simple rectangular element with corrugated metal pipe voids. You can see the rebar projecting from the footing. Simple, you set this to grade, you shim it, and you fill it with concrete. A very simple, easy connection that is very inexpensive. Okay, moving on. This next connection, again, this came out of research that was included in the AASHTO LRFD guide specifications for ABC. This is now we're looking into a socket connection. Now, AASHTO defines a socket connection as when a portion of one element projects into a pocket, into a void in the adjacent element. So the first one we'll look at is a connection S2, which is for integral abutments, where essentially we set the precast abutment stem over the top of either driven or drilled piles, or it could be a drilled shaft, it could be whatever your pile choice is, and the corrugated metal pipe void connects the two up. Very simple connection. It's easy to execute in the field. The photo shown on the right is a small bridge in Massachusetts, Mountain Road over Hartwell Brook in Charlemont, Massachusetts, which was an ABC project. It's on a dirt road with very low ADT, but it was an experimental project that Mass DOT did to see how these details worked, and they did work well. No issues at all with construction. So the key is the corrugated metal pipe void receives the pile. This next detail came out of Washington State. I love this detail. It's one of my favorite ABC details out there. This is where the precast column is, the column is precast with either a corrugated end on it or even just a roughened surface on the end, and it's set on a leveling pad, and you pour the footing around the column. The key thing in here is there are no dowels projecting from the precast column into the footing. The connection is made through the roughened column end and the bearing action of the column against the surrounding concrete. The best analogy to this detail is a mortise and tenon joint in timber design. And if you've ever been at old barns, these mortise and tenon joints work very well. And the concept here was we'll do it in concrete, and it works well. This is a high seismic connection. It can be used in high seismic zones, and it was developed under a federal Highways for Life project in Washington State. So take a look at the footing. So we essentially can set the column in the footing. We have to cut several bars and relocate them. So the darker bars are the bars that have been added to the conventionally reinforced footing, both horizontal, vertical, east-west, north-south, and diagonal bars in the corners to control cracking. You might think this is a complicated detail to design. It's actually a fairly simple detail to design. The AASHTO guide specification does cover full design provisions for this connection. And on the right side of the screen are showing a computer rendering of a pre-construction and then the actual construction of the column on the lower detail. What's great about this is the contractor can pre-tie the reinforcing in the footing ahead of time and simply set the column down on a leveling pad and pour concrete immediately. So it's a very fast construction, great for high seismic, and it's simple, easy to build. As far as design of this thing, again, the AASHTO guide spec has full design provisions for this particular connection. The two graphics shown on the screen are snippets from the AASHTO guide spec, and it's the full set of calculations can be followed in the NCHRP 12102A training module 2, which includes a fully worked example for this connection. Let's take a look at what it might look like if you built one of these. I mentioned before, you could corrugate the end of the column, but you also could just go with exposed aggregate. The provisions in the guide spec cover both of these. On the right, we show an X-ray view of the column. We typically use headed reinforcing bars in the column. The bars have to be developed within the column itself. The ABC guide spec does cover provisions for development of headed bars, so that's covered for you as well. Note that the confinement bars are not shown in this X-ray view for simplicity. And showing how to build a footing. In this case, the green bars are your traditional bars you would have if it was a cast-in-place footing with a cast-in-place column. The red bars represent bars that are either shifted or added to complete this connection. You set the column, you pour concrete, take away the forms, and you are finished. Simple, simple connection, very cost-effective. Okay, last couple sheets we'll cover now. This sheet covers keyed connections. As I mentioned before, we have a K1 connection, which is a key that's filled with concrete. We recommend using concrete for a lot of these connections. You just have to make the joint a little wider, and you can fill them with concrete, although you could use non-shrink grout if you want to make the connections narrower. This is what I talked before about the vertical keys. One thing you may want to do if it's an abutment, you may want to seal the back of the joint with a neoprene sheet to waterproof the joint if you desire. It's not really necessary, but some engineers have chosen to do this. We came up with this nice little table that calls out the width of the joints required for different materials used. So if you use non-shrink grout, you can use an 1.25 inch joint. If you use 3/8 inch stone concrete, you need an 1.5 inch joint. And if you go with a standard 3/4 inch stone concrete, you go to 2 1/8 inches for the width of the joint. The last couple sheets are devoted to tolerances. We have recommended tolerances here for pier elements, including caps, columns. And then we have the last sheet are recommended tolerances for wall elements. This would be abutments, cantilever abutments, integral abutments, and we have grouted couplers shown here as well. In the lower left, you'll see a detail for sizing the void for an integral abutment for a driven pile, and the recommended size of that void is based on the driving tolerance of the pile combined with the size of the pile, and you can size the void diameter. So that wraps it up. So in conclusion, the PCI Northeast Bridge Committee has been around for over 30 years. I've been on the committee for almost all 30 years. I started without gray hair. Now I have lots of gray hair. But the key thing I'd like to always point out is the committee is comprised primarily of DOT engineers, fabricators, and consultants. So it's not an industry committee. It really is a collaboration with DOTs and fabricators and consultants. I like to say we started ABC before there was ABC. It's not totally true, but it's pretty close. And we've established numerous documents on ABC guides. The latest is the 2022 guides for precast substructures using ABC. So this document, again, is available. It's based on the 2018 AASHTO LRFD guide specs for ABC, and it's available for free at PCINE.org. Unfortunately, the AASHTO ABC guide spec is not available for free, but you can purchase that at the AASHTO bookstore. And with that, we'll entertain any questions that might be out there. Thank you.
All right, thank you, Mike. At this point, we'll turn it to Paul Lyles and Jugish Kapoor, who will moderate the question and answer period. So, Paul, it's all yours.
Okay. Thank you, Mike and Rita. It's really quite some document. And we have a few questions. There's still some coming in. But anyway, we'll go ahead and get underway now. We have questions that came in before the presentation, and certainly some that came in during. But I've broken them down into maybe say general questions first, and this one came in beforehand. Are there any surprising recommendations in this guidance document that you would like to discuss, and maybe the reasons why?
I don't know if I'd say surprising, but there's a couple things that we commonly see people not mess up with, but they don't take into account. I mean, tolerances are so important. So I don't know if I call that a surprise, but really we want to make sure that people focus on tolerances, because if something's going to go wrong with a prefabricated project, it's going to go wrong with tolerances. So that's important. As far as surprises, I wouldn't say anything is really a surprise. We're offering numerous connection examples here. So if there's a detail you don't like, you can choose one you do like, and that's a huge difference in compared to the previous documents we had.
Okay. Another question that came in beforehand, can you provide a comparison of precast versus poured in place specific to environmental impact, carbon reduction, and cost?
Yeah. The focus of this presentation was really on connection details. It really doesn't cover environmental impact. Not that that is not an important subject. It would be an interesting subject in the future, but really was not the intent of the coverage for this particular webinar.
Okay.
Yeah, and I do want to say that the
go
industry is obviously looking to try to come up with new mix designs, trying to use obviously low carbon cements. So there is a direction going forward. Obviously, everybody knows that concrete has a high carbon footprint, so industry is looking at how to reduce that going forward. And I think over time you'll start to see things between new mixes and new techniques help reduce that. So.
Okay. Another question came in beforehand. Does PCI guidance vary greatly between regions?
Mm-hmm. Well, the key thing is we made it clear in this presentation. This is the PCI Northeast guide, which is it's New England plus New York State. However, if you notice, really these details are applicable to just about any part of the country, and we are actually looking to make this more of a national document. So this is not just a Northeast document. This is a national ABC document and can be used as such. That being said, if anyone wants to use a detail in this document, I really do. You have to work with the owner of the bridge, meaning the DOT, to make sure that any detail you propose is acceptable to them. Just because it's published doesn't mean it's approved in every state. So that's an important aspect, to work with your owner on any ABC project, and really sitting with the owner and going through all the options for each connection. Pick the option that is most comfortable the owner has and go with that.
Okay. There was a question that came in: was this system approved for use on Florida DOT projects?
I'll just say ditto, same thing. I'm not aware of it being approved, but again, feel free to present it to the DOT if you want to use one of these details in one of their designs. Okay,
and then there was the question that came in beforehand: could you comment on the importance of redundancy in bridge structures?
Redundancy is a hot topic in AASHTO. It always has been. My career started in 1983 when a non-redundant bridge collapsed in Connecticut. So I am keenly aware of redundancy. That was not the topic of today's discussion. So really, today was really just focusing on substructure connections, the substructure details.
Okay. There's a question that came in beforehand on what are the precast bridge unit life cycle expectations, and how does this compare to cast in place, maybe a concrete deck with potentially less porosity?
Yeah, the question was with respect to PBUs, which we refer to as prefabricated bridge units, which are two beams with a precast deck on top, essentially making a double T. They're also in AASHTO, they're referred to as modular deck beams. So there's two names out there. The reality is, in most cases, the deck that's cast on top of those beams is typically standard state DOT deck concrete. So the durability of that concrete should be equal to any cast in place deck out there. The closure joint materials, there's different materials being used. Ultra high performance concrete has been used, and high early strength concrete has been used. And our experience to date is those mixes tend to be even more durable than normal deck concrete because they typically are very high strength, which usually results in very low permeability. So the general answer to the question is we've got these things in service, at least 10 years in service, and the performance has been equal to or better than cast in place concrete. So there really is no letdown in durability going to precast.
Okay. We had a question that came in during the presentation. It's sort of a general question, but it says, are there any issues with precast fabricators developing forms? They're interested in reusing them on other projects without getting into too many custom forms for just one project.
Yeah, well, you'll notice a lot of the details have simple rectangular elements. We do that quite on purpose. The reality is, in most cases, the fabricators are going to use wood forms unless it's a large project where they're going to have a lot of repetition. You'll notice also the columns we're showing are octagonal. There's a reason for that. That's the octagonal columns can be designed and detailed as if they're round with spiral reinforcing, but the intent was an octagonal column, let me back up, a round column has to be cast vertically. You have no choice. You have to cast it vertically. An octagonal column, you can lay the form on its side and leave one facet of the form open to the air, and you can pour the concrete in the side and finish off that one surface, which really greatly accelerates the production. You can actually have a form, say if you had a project with lots of columns, you can make a form 100 feet long and cast 7 or 8 columns at a time. We haven't seen that yet because prefabrication has not gotten that popular. But to try to standardize things, it's very difficult to come up with standardized cross sections that would justify the manufacturing of steel forms. So the most part, we're seeing wood forms used at this time in the industry.
Yeah, okay. The standardization would be difficult. It's just that every bridge tends to be unique unless you can actually come up with a design that could be repeated at several locations, which typically does not happen. So that's why the standardization of the elements is difficult.
Mm-hmm.
Okay, we're going to get over to some specific questions now. These came in beforehand. I've got 2 of them here that are seismic related. Can you comment on prestressed prefabricated bridges in seismic zones and design of connections in seismic zones? You mentioned some of that during your talk.
Yes, the guide specification for ABC, which is shown on the screen, does include provisions for seismic design. Now, granted, this document was put together in 2018. There was limited research on seismic connections, but there was some research. So there are a handful of connections that are included that are seismic connections. The key thing is grouted couplers are difficult because, especially when you're using displacement-based seismic design, because the couplers affect the geometry of the hinge when it forms. So a couple options are available. One is putting the grouting couplers in the footing. Other options include the pocket and socket connections that we described that are seismic connections as well. So there are a number of connections available for high seismic regions. Not as many as non-seismic regions, but still there are some out there. There also is research ongoing, and recently completed research and ongoing research of other ideas out there for precast columns in high seismic zones. So at some point in the future, the AASHTO committee might supplement the guide spec to add those details in. But the key thing to get across is there are details for high seismic regions. There are options available. Grouted couplers are not the only option. I know a lot of the seismic states are not keen on grouted couplers, and I get it. I don't have a problem with that. But I mentioned those socket connections and some of the pocket connections we showed are perfectly adequate for high seismic regions. And the guide specification has design provisions for those capacity protected and strength design connections using those details. So we have specifications to cover that.
Okay, and then there was a question here about came in beforehand. What are the latest guidelines for designing pipe pin connections between column and superstructure in high seismic areas?
Yep, I'm aware of that detail. Unfortunately, when the guide specification was written in 2017, that research had not been completed. When the guide spec was written, what we did is I was the principal author of the guide spec and the principal investigator on the research project for it. We gathered all the research that was completed in the US on connections of precast and connections in general for ABC, and we vetted each connection to see if it would make it into the guide specification. That particular detail, the research had not been completed at the time, so it didn't make it into the document. It doesn't mean it's not a good connection, it's just something that didn't make it into the guide spec. And for our PCI Northeast Committee, we wanted to make sure that we only included details in our guideline that are included in the guide specification. We didn't want to go out and show a detail that isn't covered by AASHTO. We wanted to make sure everything was covered by AASHTO, so users of the document could design and detail according to AASHTO.
Okay, we'll look at some precast footings. The question came in beforehand about what are the difficulties in subgrade requirement preparation for precast concrete spread footings?
Yeah, the key thing is we've seen people try to prepare the subgrade perfectly level and set the footing down on top of the subgrade. It can be done, but it requires a high level of accuracy of getting that subgrade leveled off, and there's no adjustability. So we recommend setting the footing 3 to 4 inches above the subgrade. So normal preparation of subgrade can be done with the normal tolerances you have for preparation of subgrade. Set the footing 3 or 4 inches high on shims or leveling devices, and then fill that void with flowable fill to complete the connection. And it really is a connection. You're connecting a footing to the subgrade. That is a connection. And the flowable, this is in the guide spec, but it's also, the key thing is, as I mentioned, the pressures that are underneath footings are in the magnitude of 100 to 200 PSI, not KSI, PSI. So it really, you don't need a 5,000 PSI grout. You can use non-shrink grout. It costs $6,000 to $7,000 a yard, but you can use flowable fill that costs a fraction of that number. And it's very flowable and it's perfectly adequate structurally to take the loads that we typically see under footings.
Okay, that was some of the difficulties. The question came in beforehand, what is the proper foundation preparation for precast concrete footings?
Yeah, like I said, the normal preparation for if you're building on soil, whatever you would do for cast in place construction is appropriate. We have had cases we've talked about if you're on bedrock, you may have to do some pre-blasting and maybe even pour what we call a mud slab, which is a low strength concrete slab on top of the uneven rock surface to give you a table to work off of. That has been done by New Hampshire DOT has done that before. So if you have a case of a spread footing on rock, a little more preparation, you probably got to create a level surface, a relatively level surface to put your precast footing on.
Okay, we had a lot of questions about joints. We'll get into those in just a second, but there was one here I wanted to ask you. This came in during the presentation. Are there any successful examples of use of a precast pier cap with a secant pile wall to allow for accelerated top-down construction? The
Okay.
secant pile wall would act as the abutment wall.
I have never seen it happen, but I can see how you could do it. You could have a secant wall with bars, dowel bars projecting out of the top of the secant wall, and you could set a precast cap with corrugated pipe voids. You could definitely do that. So take the details I covered with wall panels, wall piers, or a wall abutment, cantilever wall abutment, having dowels projecting out of the secant pile wall, set a precast cap on top. There's no reason why that wouldn't work. I've never seen it done, but theoretically it would be easy to do.
Okay, we got a bunch of questions on joints that came in beforehand, and we're going to try and go through these pretty quick because we've got a bunch more questions that came in during the question and answers.
Keep rolling.
Okay. Do you need to take any additional requirements for precast substructure connection details underwater?
Yeah, I wasn't sure if the question, I saw this question before, whether it meant installing it underwater or having it underwater in the final condition. Okay, first half, if it meant installing it underwater, I know of no connection that can be installed underwater. So you have to dewater the connection to make it. As far as exposing it to water afterwards, these connections are truly emulative of cast in place construction. In cast in place construction, we have construction joints in every structure we build, and sometimes we expose those joints with their underwater. The same precautions would follow here. There's no reason you couldn't have one of these connections in an underwater, in the final condition be underwater. The durability has been proven to be equal to the cast in place construction.
Okay. Or is there an inspection process to verify that the precast member connections are 100% successful?
Yep. I'll cover a couple different ones. For grouted couplers, the grout is poured in the bottom of the coupler and it comes out the top. That ensures that you're getting the coupler completely filled with grout. So that's one option. Two, you can, for very complex void grouting, that might be a blind void that you can't see. Some states like Texas DOT have specified that the contractor has to build a mock-up, pour the grout into that complex void, and they break it apart a couple days later to prove that they're getting the grout into the void appropriately. That's another option. But as I said before, a lot of the details we presented here today are not blind connections. Some of the socket connections and pocket connections are very easy to inspect during construction because you're filling a void that's exposed. You can just look and see the hole being filled. So if you're concerned about voids getting filled properly, go to another connection that doesn't have that situation. Otherwise, we recommend, and the ABC guide spec does recommend mock-ups for complex joint grouting and void grouting.
Okay. Is there any dry connection to connect prefabricated columns to precast footings?
The answer to that, I know of none that have been studied. There's nothing, we didn't include it. There's nothing in the guide specification. They may be out there, but the ABC guide spec does not cover that.
Okay. What type of mechanical connectors have worked better in construction?
What type of mechanical connectors? Now, the grouted couplers work well. You have to be tight with tolerances. You got to make sure your tolerances are correct. But they have worked. They've been in the industry for probably 40 years. They're not a new technology. People get nervous about grouted couplers, that they're not structurally adequate. AASHTO defines a mechanical connection as a connection that can develop 125% of the specified yield strength of the bar. Well, in the ABC guide spec, we actually include a higher level grouted coupler, type 2, which is in the ACI code. And this is ability to develop 100% of the specified tensile strength of the bar, meaning you could just about break the bar. So these are very robust connections. They function essentially the same as a lap splice, where the force transfers from the bar to the coupler to the bar and through. Lap splices, there's no mechanical connection with lap splices, yet they work. So that if you, I always tell people, you can trust the lap splice, you can trust the grouted coupler. I'm trying to think of a question. That's probably the biggest one that people talk about with connections. The rest of the connections, as you saw, were pretty straightforward and easy.
Okay. What are some rules of thumb for precast substructure connection details?
My rule of thumb is, one, take into account tolerances. Tolerances are really important, okay? And two, work with the owner to pick the right connection for your bridge. Make sure the owner's okay with it. That's my rule of thumb. Okay. They all work.
Also, talk to the fabricators. They'll provide you input on connections and what, because they're going to have to construct it. So if you have questions on constructability, it's always best to talk to a fabricator early on too. So,
okay. You know, I always say, Paul, you know, we figured out how to do ABC in the United States. What we're trying to do now is figure out how to do it better, faster, cheaper And hopefully the details we presented today, we can argue about some of them, but quite a few of the details are very simple, very easy to execute, very easy to fabricate, which will reduce the cost and reduce contractor concern over assembling a precast structure.
Okay. Were there any adjustments made to the connection details to reflect the differences in UHPC mixes in the Northeast versus elsewhere?
Okay. Great question. The ABC guide spec for AASHTO includes a section on UHPC, both for design of connections and for UHPC mix design. The specification for design is based on work done at Federal Highway. They issued a tech brief on connections with UHPC. Federal Highway doesn't issue details that are specific to one brand of UHPC, a proprietary brand. What they do and what we have included in the ABC guide spec is a performance specification for UHPC. And there are about 6 criteria that the material must meet to be classified as UHPC. It has to do with the steel fibers in the mix. It has to do with the final strength of the mix. And there's items for shrinkage and such, so on and so forth. So the key thing is the details included in these guide details and in the ABC guide spec for AASHTO are based on non-proprietary, essentially performance-based specifications for the UHPC. And what does that mean is if you have a local UHPC mix developed by, say, a university, a lot of states have done that, these details and these will work with those mixes as well, as long as they meet the Federal Highway requirement, or I should say the AASHTO requirement for what UHPC is. There's another document about to be published by AASHTO on UHPC, so the provisions for UHPC might change slightly. So that hopefully will be published this summer. And when that comes out, I would recommend, again, looking at that. But again, we're trying to come up with specifications that are not based on one particular brand of UHPC. We're trying to keep it general to all types of UHPC that meet those requirements.
Okay. What assumptions were made regarding lateral loading during development of connection details?
Well, you know, the key thing with any connection is you design it for the forces acting on it. And the AASHTO guide specification has provisions for designing for forces both axial, transverse, and longitudinal. A good example would be, say, a column connection where you can have biaxial bending and axial compression. And all of the provisions that are in the guide spec cover that. So it basically be the same as cast in place design. You can account for lateral loads as well as longitudinal loads, as well as vertical loads and shear.
Okay. What are the major design differences between precast and cast in place connections?
I love that. I love this question. Okay. I do a lot of talking, as you can imagine. I go around the country and I always ask the question, say a precast pier. I'll ask everybody in the audience, raise your hand if you know how to design a cast in place pier. And they all raise their hand. And my response is, congratulations, you now know how to design a precast pier. Really, the design is the same. You still do your same design of the pier. It's still a reinforced concrete structure, and we are designing these connections to emulate cast-in-place construction. And virtually every connection we showed today, the connection design is very straightforward using the forces acting on those connections. And really, people are mystified by precast. It's really not that hard to design these things. And the AASHTO guide specification, and when you open it up and read the provisions, you'll actually probably say like, wow, that was a lot simpler than I thought it was going to be. And for some of these connections, like these socket pocket connections, the design barely changes from cast in place.
Okay. A couple cost questions, and I'm going to turn it over to you, Gash. The first one was transportation costs are high for precast concrete. To what extent is the industry constrained by geographic markets?
Yeah, I like this question. Our committee was concerned with, you'll notice the earlier version of these guide details included a lot of precast footings. Our fabricators made it clear footings can get very heavy, very difficult to move, and very expensive to move. So it's not just shipping it, it's also what size crane you do to erect it. So we have given guidance on keeping the weight of these pieces down, and we have a recommended maximum weight, around 30 tons we recommend. But that's why we developed a lot of details with cast in place footings, because footings are probably the most difficult thing to move and ship, especially long distances. So we wanted to give options, and if shipping a heavy precast footing in your region is difficult and expensive, we gave you an option with cast in place to make it work without that heavy footing.
Okay. And finally, what is the cost difference of cast in place concrete substructures compared to precast concrete substructures?
Well, I hope with these new details, the price is going to come down and they're going to be very cost effective. But there is one element that I am confident is less expensive with precast than cast in place, and that would be pure caps. I always tell people, if you want to dabble in the world of ABC substructures, start with a precast pure cap. Pure caps with cast in place, think about it. If I have a pure cap that weighs 1,000,000 pounds, some of these pure caps weigh 1,000,000 pounds. I have to build formwork at elevation to support 1,000,000 pounds of wet concrete. I have workers working at elevation with fall protection up in the air. So very expensive forming, very expensive labor to get this thing done. Precast, I set the piece in 15 minutes and I'm out of there. So we have heard, and I know Mary Lou's told stories in Texas where contractors have proposed precast pure caps where cast in place was detailed because it was less expensive. So that's the one thing I could say when it comes to substructures. Precast pure caps are probably less expensive. I'd also say our precast integral abutment details are painfully simple. My guess is they are probably cost effective as well.
Okay. It's about 13 after. We said we're going to go to 20. I'm going to turn it over to Jugash, and he's going to go ahead and ask some of the questions. We got a bunch of them that came in after a little while. So anyway, go ahead, Jugash.
Thank you, Paul. Mike, question number 1. Which states use precast the most, and which states are not so open to it?
It comes down to superstructures and substructures. We're still not seeing widespread use of precast substructures, which is why we published this detail. States using a lot of precast in the Northeast. We do quite a bit of precast in the Northeast. States like Massachusetts, Connecticut have done quite a bit. Maine has done some as well. Vermont does quite a bit as well. So the Northeast is kind of a little hotbed of precast, including substructures. You go to states like Utah, they do tons of precast work out there. A lot of precast construction there, but really it's across the country. I am amazed, not amazed, I'm very proud to see that virtually every state in the country is doing some form of ABC using precast and prefabricated elements. This phenomena of ABC has really taken off, and you know, it's a testament to the hard work of a lot of people, including Federal Highway, FIU, Mary Lou Rawls, I'll give Mary Lou a credit here, has been pushing this for years, and people are really reaping the benefits of all that hard work.
Okay, thank you. Next question. For the socket connection shown, how is the plastic hinge developed at the column footing connection as the required confinement reinforcement is not provided?
I'm not sure which connection they were talking about. You can provide confinement reinforcing for everything I showed. It might not have been shown in some of the graphics, but like, yeah, I think they might be referring to the wall panel to footing connection. You can add confinement steel to that detail. You can add those bars and show those bars in there. You can confine every detail I showed. So maybe I wasn't clear in the presentation, but there are ways of confining reinforcing for all of the details shown.
Okay. Thank you. Next question. In addition, as time has passed, have there been any durability issues with the use of grouts and particular details as they have entered working life?
Yeah, I would say we have seen nothing in the way of problems. Utah DOT inspects all their ABC bridges every 2 years. We've done 6 of those inspections. We're going to do our 7th one this summer. The performance is every bit is the same as cast in place construction. And like I said before, we're emulating cast in place construction. And I've heard people tell me all the time, I don't like joints in my structure. Joints are going to be a durability issue. We're going to have problems with joints. The reality is every cast in place structure that gets built has joints in it. They're called construction joints. So we've always had joints in our substructures. Having joints in precast substructures really does not change the durability equation at all. So I say that, I keep saying it. We haven't seen any issues manifested in the field. As far as grouted couplers, one of the earliest bridges built with grouted couplers is in Florida. It's called the Edison Bridge. I'm saying 30 years ago. It's been out there forever over a saltwater bay. This thing, it's a corrosion experiment with a highway on top of it, and it's performing well. So we have a lot of track record on these connections, and they really do perform every bit as good as cast in place.
Okay, next question, Mike. Any issues with key joint between precast cantilever abutment regarding temperature variations, especially in Nordic regions?
Yeah. Well, the key thing is we've detailed joints that are filled with grout and joints that are not filled with grout. And we have notes in those first 5 or 6 pages that talk about if you want a true expansion joint between two pieces, you can fill the void with a foam, a sprayed in foam, to allow the structure to expand and contract. The key is you want to follow the AASHTO LRFD specifications for joints, which I believe have a contraction joints at 30 feet and expansion joints every 90 feet. State DOT bridge manuals sometimes have slightly different numbers, but there's no reason. We have details for both grouted joints and non-grouted joints to accommodate both contraction and expansion situation.
Next question, why is the diamond-like shape necessary for key joint? Won't a circular, semicircle portion chipped off from each adjacent wall stem be more efficient or have less stress concentrations? I think we can do a backer rod there.
Yeah, well, I think I can understand what they're describing. The answer is yes. The key thing on our committee is we have fabricators in our committee, and we ask them all the time, what's the easiest joint to fabricate? And the key joints are fairly easy to fabricate, and there has not been an issue with stress concentrations and failing of these joints. The research done for the AASHTO guide specification was based on essentially key joints. There are some diamond-shaped joints that have been tested as well, and they perform well. The key thing is we do recommend in both the guide spec and our details that you can come up with slightly different configurations for joints if you desire. They all seem to function fine. And a half round joint, it would work. I'm sure it would work. But our fabricators have honed in on the key joints that we show.
Okay. Next question, how would you repair or retrofit the precast connections, say after a seismic event?
Yeah, there has been quite a bit of research on retrofit of connections. Caltrans has done a ton of research on post-earthquake retrofits. Essentially, these connections function the same as a reinforced concrete connection. Even with the grouted couplers, at the end of the earthquake, you'd have the crushing of the concrete you'd normally get in a plastic hinge zone. And essentially, if the bars are still intact, the same procedures used to retrofit those connections after the earthquake would still be applicable. Again, other details we showed, the socket connections, where it really is the same as cast in place in the hinge zone. So the same retrofitting methods that have previously been used would be applicable to those as well. So that socket connection where the column is set into the footing and the concrete's cast around the column, the retrofit would be exactly the same as it would for cast in place.
Okay, Mike, I am out of time, but there were a couple of questions which we will answer on the web.
Yep.
So I'll turn it back to Attorod. Thank you so much.
Thank you.
Right. Okay, thanks, Mike. Thanks, Rita. Thanks, Paul and Jugish for moderating. It was a great webinar. So on that note, we are gonna end the webinar today and hope to have everyone back with us on March 16 for the next webinar. So long.